All right, so today we're going to get started on a formal discussion of probability distributions. This is where things can get a little bit tricky, but I promise you, if you stick with me, you'll be able to understand it. So, just to review, a quick reminder of random variables. Remember that we're just going to be talking about discrete random variables, and we notate our discrete random variable with a capital X, and those discrete random variables can be found by simply counting, unlike continuous random variables that are measurable. We call it a random variable because it's the result of a random process. It's not systematic. Variable x can take any value in the domain 0, 1, 2, 3, 4. That's just one example. Okay? And also remember that we can use a table to display probability distributions. So what do I mean by that? Well, maybe your discrete random variable x represents the number of falling percolators. So you have 0 falling percolators, 1 falling percolator, 2, 3, and 4. So when you're looking at the probabilities, what you're really looking at is the probability that x is equal to 0, that x is equal to 1, that x is equal to 2, that x is equal to 3, and that x is equal to 4. The 5 probabilities must add to 1, and they must each satisfy 0 less than or equal to the probability of x, that random variable x, equaling x, little x, that's a value, right? Such that that is less than or equal to 1. So in other words, your probability has to be in between 0 and 1, which we know is true about probability. So knowing them establishes the probability distribution of x, since the table then shows how the entire probability of 1 is distributed to each value of the random variable in its domain. So these numbers here, those are values of your random variable represented by little x, right? X sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. And lastly, a discrete probability distribution is the set of all possible values of a discrete random variable, a subset of the integers, together with their corresponding probabilities. All right, so this reiterates some of the points that I already mentioned several times, but I want us to focus in on, once again, the difference here between the different variables that you see, the capital X and the lowercase x. So the probability that variable x takes on value x is denoted by the probability of big X equaling small x, right? Big X is a random variable. Little x is a value that is taken on by that random variable, right? Maybe it's 1, 0, 3, 4, etc. So I'm not going to reread all of these things. You can go through the notes and reread this section here, but that just talks about the basics of probability and the sums equaling 1. Remember that we can display probability distributions on tables and graphs. So we've got this table here, right? You've got the different values that are represented by x, and you've got the different probabilities, right? That random variable is 0 or is 1 or is 2. And then you've got that same information being displayed on a bar graph, right? And then you've got this probability distribution diagram as well with the little dots. So there is such a thing as a uniform discrete random variable, and that's when all of your random variable x has the same probability 1 over n of occurring. Then x in that case describes a uniform discrete random variable. So a very easy example of that is a die, right? So when a die is rolled, the value of x are 1, 2, 3, 4, 5, and 6. So each value has the probability 1/6 of occurring. So 1 has a 1/6 chance of occurring, 2 has a 1/6 chance of occurring, etc. When you add all those together 6 times, you end up getting 1. So that makes sense that it's a probability distribution. And because they're all the same, we can classify it further as a uniform discrete random variable. By contrast, if two dice are rolled, the sum of the resulting numbers y is not a uniform discrete random variable. And on the notes key, I wrote out the sample space for you, and you will see one in one of our next examples here. But you can clearly understand that, for example, getting the sum of 12 is going to be different than getting the sum of 4, which you can get with a 2 and a 2 or a 1 and a 3. All right, before we get down to brass tacks here, let's take a look at example 17. It gives us a function and it says show that the function defines a discrete probability distribution by constructing a table of values. So this question's a bit odd because we don't usually think of probability questions as functions. But remember, a function just produces an output for a given input, and it's such that every input is matched to exactly one output. That's what a function is, and so we can actually define discrete probability with a function. So how do they show that? Well, they plug in all of the values in the given domain, so don't forget to pay attention to the domain. It's in between 3 and 7, including 3 and 7, and they plug it in and they get their outputs: 115, 215, 315, 4 over 15, and 5 over 15. Well, what happens when you add all of those up, those output values? Well, it equals 1. Therefore, we can say that the function defines a probability distribution because all of these function output values produce fractions that, when added together, equal 1. So they could represent probability distributions, right? A probability distribution is exactly what the name implies. It is a distribution of probabilities for a given random variable, in this case t. Now, of course, you can display this information on a bar graph, which they do here, and notice that the x-axis represents t and the y-axis represents f of t. And you want to label the graph. So the x-axis is easy to label that as t, and the y-axis, that dependent variable f of t, can be represented as a probability distribution, so they have that represented here as p, the probability of t equaling little t, right? That random variable t equaling some value little t. Those values, of course, being 3, 4, 5, 6, and 7. All right, so you try example 2. A magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, 5% purchased 5. Let X be the number of magazines sold to a randomly selected customer. State the possible values of X, construct a probability table, graph the probability distribution, and find the mode and median. So I will actually help you out with part D, but go ahead and give A through C a try on your own. All right, so hopefully you got these answers. So it states, state the possible values of X. So the possible values of X are 1, 2, 3, 4, and 5. In other words, that means that X sub 1 is equal to 1, X sub 2 is equal to 2, etc. And X sub 5 is equal to 5. For a table, we can represent these values here, 1, 2, 3, 4, and 5, as I have. And then we can find the probabilities that are actually given to us in the problem. So 23% purchased 1 magazine, 38% purchased 2, etc. So I just have that labeled here, right? So I have it on a table, and now I need it on a graph. So I labeled it. I have my X and Y axis labeled, right? I've got that little X here, and I've got the probability of the random variable X equaling the value X for the Y axis. And now I want to find the mode and median. Now, really quickly here, remember, as we discussed previously at the beginning of the notes, that a discrete random variable is a result of a random process. Notice that the random process here is that you are selling magazines to a randomly selected customer. That's the random process that needs to take place for this particular problem. That's just important context to know for the future. So lastly, D says find the mode and the median. So the mode is pretty simple because we can just look at the highest probability. And the highest probability here is 38%. So 2 magazines. So for D, 2 magazines, that is going to be the mode. Now the median, that occurs at the 50th percentile. So we've got percentages here, right? So we just have to keep adding in ascending order until we get 50%. Well, if we have probability 1, well, that's equal to 0.23, so that's not quite 50%. We add to that probability 2, so we add these two things together. Well, probability 2 is 38%. Well, when you add those two together, you get 61%. Well, that's past 50%, right? If the median lies at the 50th percentile, where is it going to be? Well, it's not going to be at 1 magazine, right? Because that's only 23%. It's going to be at 2 magazines, right? Because 23% and 38%, well, that's going to give me something that's past 50%. So the median must lie here. So 2 magazines must be the median. So 2 magazines at 2. Okay? All right, so our last and most challenging problem deals with a fair cubical die and a fair tetrahedral die. They're thrown, and the discrete random variable S is defined as the sum of the numbers on these two die. Construct the probability distribution of S as a table of values, a bar chart, and a piecewise function. So I went ahead and did A1 and A2 for you here. So you've got the results of your cubical die and your tetrahedral die. So here is your cubical die and here is your tetrahedral die. And you are finding the sums. So 1 and 1 make 2, 2 and 1 make 3, etc., right? And then you're using the results from A to create the probability distribution table. So what's the probability of getting a sum of 2, 3, 4, all the way up to 10? So let's interpret this. So when you roll both dies, you have a total of 24 possibilities, right? It's 6 by 4. It's a 6 by 4 table, so 24 possibilities. And then you add those possibilities together to get something between 2 and 10. So out of the 24 possibilities that you have when you roll a 6-sided die and a 4-sided die, 1 out of 24 combinations is going to result in a 2. 2 out of 24 combinations is going to result in a 3, etc. And then lastly here we've got the bar chart, right? So that is just another example of how we can use these different visual displays, and it mimics what we did before. So you have those possibilities 2 through 10, those sums, little s represented in the x-axis, and in the y-axis you've got that probability of the random variable equaling the value s displayed there. Okay, so now we're going to move on to part 3, developing a piecewise function. So go ahead and try this on your own. So you should notice a pattern between each of the different values within the domain. So for example, the sum 2, 3, and 4, well, the numerators, they just increase by 1 each time, and the denominator stays 24. 5, 6, and 7, the numerator is all 1, and the denominator is all 6. And then, lastly, 8, 9, and 10, we've got this denominator being 24, but we have a numerator decreasing 3, 2, and 1. So let's make this piecewise function. So first of all, we're going to start with f of s equals. So we know we're going to do something with s, and we're going to divide that by 24. Well, if s is 2, how do we get 1 from 2? Well, we subtract 1. Does that also work with 3? Yes. 3 minus 1 is 2. Does that also work with 4? Yes. 4 minus 1 is 3. So I've taken care of those first 3 possibilities, and that's for a domain of 2 to 4 inclusive. So now we're looking at that second set. Well, they're all 1/6, so to me, it's just 1/6, right? It's from 5 to 6. Oh, sorry, 5 to 7. And then lastly, 3, 2, and 1. So we know that it's divided by 24, just like that first part of the piecewise function. But the numerator is what's a little bit tricky. So if we look at s here, if we start with s being 8, well, it's not 8 minus 1 because that's 7 out of 24. We want 3 out of 24. It's not 8 plus 1 because that's 9 out of 24. That doesn't work either. So let's think about this for a moment. How can I get 3 from 8, 2 from 9, and 1 from 10? Well, it's not s minus 9, right? Because, well, 10 minus 9 is 1, but then you have 9 minus 9, which is 0, which that does not work. What else? Well, it could be 11, right? 11 minus s. Because if s is equal to 8, 11 minus 8 is 3, 11 minus 9 is 2, 11 minus 10 is 1. So you just have to think a little bit critically here about how to get those resulting patterns. And that's for the domain, of course. 8 less than or equal to s, less than or equal to 10. So that's how we create a piecewise function for this particular probability distribution. And now we're going to find probabilities, which is the actual application of probability distribution. So hopefully you can see the notes here. If you can't, just follow along on the PDF and listen to this while I talk through it. The first one is we want to find the probability that the sum, that's what that random variable represents, the sum is greater than 2 when we roll those dice, the tetrahedral dice and the cubical dice. So all I have to do is use my chart, right? That's the point of making this distribution chart here. Because for these types of problems with this more complex sample space, this visual definitely helps me solve the problem. So what are all of the possibilities greater than 2? Well, that's going to be 3 through 10. All of those are greater than 2. Well, those probabilities are here. You could definitely add them all up one by one, or you can just say, well, what's the only probability not represented for this particular situation? 1 out of 24. And if they all have to add up to 1, you just take 1 minus 1 over 24, and the that difference, what's left over, is going to be 23 out of 24, which is the answer to this first question. Or like I said, you can add up 2 out of 24 plus 3 out of 24 plus 1, 6 plus 1, 6 plus 1, 6, etc. Because what you're saying is the probability that I land on a 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, all of those are greater than 2. Okay, so that's part 1. Let's look at part 2. Part 2 says the probability that S is at most 6. So at most 6 means 2, 3, 4, 5, and 6. So we just have to add up those probabilities, right? So we take 1 out of 24 plus 2 out of 24 plus 3 out of 24 plus 1/6 plus 1/6, which is 2/6. So we add all of those things together, we reduce our fraction, and we end up with 7/12. Okay. Now, part 3 is the most challenging one. You will undoubtedly get a question like this on a paper 1 or paper 2. So make sure that you understand how to solve this, because now we're combining this probability distribution with conditional probability. So it makes it a little bit more challenging here. So maybe pause the video and give it a try yourself. So part 3 says find the probability. So let me do this in a different color. Let's do blue here. Find the probability that the sum is less than or equal to 6 given that the sum is greater than 2. Okay, so we already know that we rolled a sum that's greater than 2. What's the probability that that is also going to be less than or equal to 6? That's conditional probability. Anytime you hear the word given, anytime you see the little bar, that means that you're working with conditional probability. So we're going to use our formula to set this up correctly. So, in other words, if I just use my formula directly from conditional probability, I know that the probability of the sum less than or equal to 6 and the sum is greater than 2 has to be the numerator, and I have to divide that by the probability that the sum is greater than 2. So all I'm doing is I'm using this notation, this formula from the conditional probability section in your notes. So go back and look at that if you're a little bit confused. Well, there's got to be an easier way to express this, right? Well, there is. So how can I express this? Well, S, the sum, is less than or equal to 6 and greater than 2. That's compound inequalities. So in other words, 2 is less than S is less than or equal to 6, right? That's the same thing. I could just put an and here, right? And an and in symbolic notation is represented by that little upside down U. Okay, so that's what I'm looking at. So in other words, I'm looking at the probability that 2 is less than S, is less than or equal to 6, and I'm going to divide that by the probability that S is greater than 2. Well, the good news is I already have this denominator up here, 23 divided by 24, so that's fine. So this is 23 divided by 24. Now I have to find the numerator, that it's in between 2, not including 2, and 6. Well, I can highlight that up here. So let me go ahead and erase this. And let's just highlight what is relevant for the numerator. So it's not including 2, right? So really what we're looking at is this. Another way to write that would be the probability that S is between 3 and 6, and just change the inequality sign there. Those things are saying the same thing. So I can add 2 over 24 plus 3 over 24 plus 2 over 6, which gives me 39 over 72, which reduces to 13 over 24. Well, you flip and multiply, you end up with 13 over 23. Okay, so not too challenging actually if you remember the definition of conditional probability and you understand that you can translate this into a compound inequality because you are just using an intersection here that is represented by that upside down U. Okay? Not too challenging. Just make sure that you practice the homework questions, and if you have any questions, please email me. I haven't been getting many emails lately, so I'm just assuming that you guys are understanding everything. Do make sure that you're keeping up with the homework. I'm going to be doing homework checks this weekend to make sure everybody's caught up. And just remember that all the hard work that you're doing now will definitely pay off. Have a great day.